Bom, boa noite a todos. Nós vamos começar a nossa transmissão. Essa é mais uma sessão do Facom TechWeek de 2021, certo? A sessão de hoje será em inglês, porque nós vamos ter um convidado internacional. Manohar Paluri is a director at Meta, also known as Facebook, and leads the organization focusing on perception and robotics efforts in the AI research. His team is part of the AI research organization, pushing the frontiers of AI and helping create breakthrough moments in perception and robotics. Prior to his current role, Manohar was leading the applied computer vision and augmented reality teams, serving image and video understanding capabilities for hundreds of products across all of Meta's family of apps, serving billions of people every day. His interests lie in pushing the frontiers of computer vision, conversational AI, multimodal reasoning. Before Meta, Manohar was pursuing his PhD from Georgia Tech, where he got his master's, and worked at Google Research, IBM Watson Labs, Sarnoff Corporation, and today he's going to share his vision about computer vision at Meta. It is my great pleasure to receive Manohar Paluri today. Manohar, without further ado, with you.
Thank you, Lazaro, and thank you for having me here. Of course, I would have loved to be in Brazil or any other place, but given the current circumstances, pulling this off virtually is the best thing to do. I hope everybody is safe and doing well. Thank you for the kind introduction. I have been thinking about what is the best way to present all the amazing work that is happening, both in Meta and in the field of computer vision, which is something that I've been working on for the past 2 decades. And I thought it'll be good to give an overview so people kind of understand all the awesome things that are going on in the field and that we in Meta are working on. So hopefully by the end of this presentation, you get a teaser of various efforts that are happening in this area of AI. At first, one of the questions that I always get asked is, why is computer vision, or for the matter AI, even important for Meta or Facebook? And when you really look at the core mission of how Facebook started, it was to connect people, to bring them close together, and provide the technology as well as means for people to do this at a scale that is unprecedented in the history of humankind. Now, to do this in a safe way and in a way that is enriching, that is innovative, and something that is more futuristic, AI becomes an essential piece of the puzzle. Without AI, many of the things that we are doing cannot be scaled, cannot be even built, and we cannot imagine systems and processes to run at 3 billion, 3.5 billion scale. Taking one step further, if you look at the evolution of the world and how humans have been interacting with machines, we really started with text and keyboard as the main mode of communication. But we're really transitioning into this visual mode of operation, whether it's to express what you're eating, where you're traveling, the time that you're having fun with your friends, making memories, sharing with others, and even talking. It's so easy these days to just switch on the camera, capture the moment, or have a video conference call, or even a virtual call like this, whether it's for work or for pleasure. So we are really moving to a world which is more visual in nature, more richer, and that actually brings up this important problem that we need to tackle, which is the machines and the algorithms that we are building need to understand this visual world in a more intricate way, in a more richer way than before. So we cannot get away by not looking at the pixels. We really need to build the algorithms and the backbone that understand this media, whether it's photos or videos, that then enables us to build applications for billions of people. And that is exactly what I'm going to talk today, so you can get a sense of how to do it. So 2 things that I'm going to focus. One, how do you design an image or video recognition system at a billion scale? Now, putting together a prototype, a demo, a small system that will work on in an offline manner or even in an online manner, but at a scale of thousands, isn't something that you can imagine doing quickly. But when you actually have to design it at a billion scale, you really have to optimize every piece of it in a way that is efficient, so you can actually run it at billion scale. And we're talking about billions every day, easily touching trillions over a period of years. And then as you're thinking about computer vision and pushing the frontiers, I'm really one of the things that we have noticed in the past is the importance of data sets. Data sets are the bread and butter of progress in AI. They actually give us the benchmarks for others to build on and to compare and to make progress. So I'm going to actually talk about two new data sets that we released very recently, which is very exciting and get us to this vision of metaverse and embodied AI. So let's talk about how do you build a billion scale image and video understanding system. When you think about Facebook, it's a social graph. There are people that are actually joining the network, that know each other, that interact with each other. And the way they interact is they write posts, which could be text. They share photos, which could be their visual moments of their life. They share videos, which are even more richer and capture temporal and spatial information with emotions and audio. One of the things that we have to do is to build algorithms to make sure we understand this text, the photos, the videos, so we can either remove things that violate our policies or show you the relevant content in recommendation systems or search systems, or build experiences like accessibility, where a visually impaired person get a notification that this is what is in a photo or this is what is in a video. So there are hundreds of such applications. And what the algorithms are trying to do is take this social graph with all the people nodes and the content nodes and make it semantic. So what we have is now for each of the photo and video and the post, we try to understand what is in it, and we try to either enforce policies or rank them. And this additional metadata makes that social graph semantic. And this is how we have vision models in production. The challenge here is if you have hundreds of product groups, you need hundreds of models, each one for each task. And here what you see is a typical convolutional neural network, which is the model that we use to understand what is in a photo. And you train one for each task, which typically takes hours and days. And if you have hundreds of tasks, you will have to do it hundreds of times. Not only that, when you actually have to run these models in production, you will have to use thousands of machines because each model is different. How do you get away from it? One of the ways to think about it is when you really look at these networks, they are hierarchical in nature. There are layers that process the input and produce certain outputs. And each of these layers is an abstraction. The deeper you go, the more general these layers are that are not specific to the task that they're trained. And the higher you go, closer to the task, the more the representation is specific to the task. So this infusion actually allows you to start building universal vision models. So if you have many tasks, you can basically leverage the same compute from the bottom layers and add new models or layers on top where you reuse the compute, but also at the same time tackle many tasks in parallel. So this is exactly how we did, where we actually have one mega neural network that is trained at an unprecedented scale of billions of photos for weeks and sometimes months. And once it's trained, we take those representations, which are hierarchical in nature, and we build branches or new models on top of that for various use cases. So when now you have to support a new use case with different outputs, you don't need to train the whole network. You basically just train the top layers of the network, which usually can be done within minutes. And that's how we are able to power photo search capabilities, newsfeed ranking, connectivity efforts, integrity, where we want to remove policy violating content, or accessibility, where we want to describe what is in a photo for visually impaired people, and so on and so forth. And the progress in image understanding has been astounding over the past decade. If you really look at how far we have come, we now have models that not just classify what's in a photo, which is a sheep or a person or a dog. You are now able to detect where in the photo these things are, so you can put bounding boxes around them. You are able to segment which pixels belong to what category. So you can say this pixel, which is blue color, is all sheep. This is pixels of a human being or a person. This is pixels of background and grass and dog and so on and so forth. And you can go one step further. You can even say this is instance of sheep 1, sheep 2, sheep 3. So you can start counting the number of sheep and distinguishing one sheep to another. And you can even have attributes. The person is wearing a hat, they're standing, the sheep is furry, or the dog is running, and so on and so forth. And you can keep pushing these frontiers. You can keep building relationships. This person is probably taking care of the herd, and you can even go fine grain. This is this particular kind of sheep, or talk about aesthetics. It's like this photo is more beautiful than another photo that might not be in focus, and so on and so forth. And if you look at the evolution of the models, we started with many of these models that are working back in 2012, and we kept building various models on top of it across the years, with faster RCNN in 2015, mask RCNN in 2017, and latest work that we have done in 2019 is actually to be able to segment everything in the photo, not just the foreground and people and objects, but even the background and stuff, which is very difficult. So in this case, we can segment, this is the sky, these are the trees, these are the buildings, and so on, which are very difficult to confine with the bounding box. And to do that, I mean, I don't want to go into the technical details, but for people who are in computer vision or AI background, what we do is we actually add new branches of models in a model that can actually predict various things in parallel. So you have a backbone model and a head that is doing instant segmentation, and you have another head that is doing semantic segmentation, and both these heads are trained together to get the holistic understanding of a photo, the background and the foreground. And these models are then used for various tasks where the image and video classification, where we have thousands of concepts that we have trained our model on that recognizes. We have models that look at faces and people and text in a very special way, because if you really look at the distribution of photos that we get, people and text are the most frequently occurring entities. And OCR models, the text detection and recognition, are another set of things. So these are all various models that we have been able to build using this framework that I just talked about and run at scale, especially billion scale. So this is a teaser video of what we actually launched almost 4 years ago now, which was revolutionary at the time, where a visually impaired person, when they actually come to Facebook or any of the apps, they actually get a description of what is in a photo, because they can't actually see like other people.
Wonder what it's like to use Facebook if you are not able to see? Turn on your sound to experience it. Screen readers, like this one, read aloud what's on the screen, making Facebook accessible to the millions of people worldwide who can't see. And now Facebook's new technology can tell them what's in the photo. Facebook, search. What's on your mind? Xiaomi Wu, March 6 at 10:14 p.m., with my college buddies in my favorite place, ready for a great weekend. Photo, image may contain tree, sky, outdoor. Demetric Sanders and 7 others reacted.
So I stopped the video because I want to keep moving, but you get an idea. Simple. So these powerful technologies can actually enable simple experiences that are game-changing for certain people. Now, if you're not visually impaired, you're going to browse Facebook or, for that matter, internet with ease, whether it's a photo or a video or a web page. But imagine the world for people who are actually visually impaired. For them, knowing what is in the photo could be the biggest difference when they actually browse Facebook, when they want to know what their friends are up to and what is going on in the world. And that is exactly what this technology actually provides. And it's just the beginning. There are many more things we could do in accessibility and in general build experiences that are more unique. So that's how you build models at billion scale. But there is one big problem that we are sidestepping. When you really look at these models and how they're built, you actually are in what we call the leftmost part here in the visual on fully supervised system. So what does that mean? To train these models, you have to actually annotate each and every photo and video with all the things that you want the model to predict. So for example, if you want the model to say, I see a car, I see a tree, I see a person, you have to sit and annotate for every photo what is in the photo, and then use all of those photos and the labels that you have annotated to train the model. This is called a fully supervised model. And this produces the most accurate models to date, but at the same time are not scalable. You will have to annotate millions of photos with thousands of categories, which goes to billions of annotations very quickly. And not everybody can actually pull that off. And more importantly, it's not a scalable way of doing things. So what we are actually pushing for, or what we have been pushing, and we have been very successful over the past few years, is moving away from this fully supervised realm to what we're calling weakly supervised, semi-supervised, and self-supervised. So very quickly, weakly supervised is you get these annotations and labels, but they are not accurate. So there is signal and there is noise. And the job of weakly supervised models and learning is to identify the signal and remove the noise, and yet still train models that are as good or better than fully supervised. The weakly supervised realm is a very interesting realm because instead of sitting and annotating and verifying every label, you just blindly throw all of the annotations and let the model figure out and be robust to the noise. In semi-supervised, you basically have a combination where part of the data is fully supervised, you get exactly the labels, and part of the data, you don't get any labels, you just get the raw data. It's very interesting realm where you can actually leverage these small amounts of supervised data along with the large amounts of unsupervised data or raw data and still build better models, because you can actually still start increasing the funnel. And then you are in the self-supervised realm, which is on the extreme right, where you really only look at the raw data and you leverage the structure of the raw data to train models. This is the holy grail, because here you're not sitting and teaching the machine every little detail. You're just saying, figure it out. Here is the data. Here is the structure of the data in the world. And you learn models, and I'll basically use whatever you have learned and apply it for various tasks. So those are various ways of training models. I want to quickly touch on weakly supervised, because this is something that has been very unique. And when we started this project, we were really not sure whether we can actually build models that will beat fully supervised. It turns out, and I'm giving it away for you, is we can, because of the sheer scale. So what we did is we took billions of photos that are public, that are shared on Instagram, and we trained a model on it. Now, it's not easy to train a model on this, because in a fully supervised realm, you basically get this photo and you say there's a cat, there's a dog, they're both on a wooden floor. That's great, you train a model. Whereas in a unsupervised realm, you don't get any data, you just get the raw pixel or the photo. But in a weakly supervised realm, you basically get a bunch of things that might be accurate, that might be inaccurate. For example, you might get hashtag cat, which is a hashtag that people use. Hashtags are used by people whenever they share photos, and hashtag cat in this case is actually a good hashtag because it's accurate and it is right. There can be a text sentence that describes a photo, a cute cat couple, for example, which is not right because it's not a cute cat couple, it's a cat and a dog. So you kind of get this noise. There are many types of noises, noisy labels. One of them could be non-visual labels. So hashtag love, which is the most frequently used hashtag on Instagram, by the way, is something that is accompanied a lot and it doesn't have a visual appearance to it. So you can't use it to train models. When people use hashtags, they're not trying to enumerate everything in the photo. So they kind of miss the labels and the model has to figure it out. And then in some cases, they might even use labels that are not accurate. Now, I'm not a dog lover or I don't know all the breeds of dogs, but I definitely know that that dog is not a husky. But the person who actually shared it actually used hashtag husky. So the job of the model is to deal with all of these kinds of noises. And that's what we were able to do. We used billions of photos with thousands of hashtags and trained very large models in a distributed way. We used what this particular work is built on ImageNet in Manohar. ImageNet is a public benchmark in image classification with 1,000 labels and million images annotated. To train a model on ImageNet, it used to take us days. The ImageNet in 1 hour, which is doing distributed training, actually allowed us to train models within an hour, which is what we use to train on billion scale. And we were able to achieve state-of-the-art performance. This is 3 years ago, actually. And now the numbers are even better. And the beauty of this methodology is before we use these models and train on much smaller scale, you would get labels that are more generic, like food or this is an important landmark, but you don't get the fine-grained information of what is in it. Whereas when you train our model in this large-scale fashion, you're able to predict that this is a cupcake, this is an apple pie, this is a Statue of Liberty, and so on and so forth. And when you look at captioning systems that are actually built on top of these models, the captions are much more, so WSL, which is weakly supervised learning, are much more richer and descriptive. And these models are actually made available for developers to build on. So if you want to use these representations compared to other representations that might not be as generalizable or as accurate, you are more than happy to, you're more than welcome to. They're available in PyTorch. This is a simple way of importing that model and using it to on your input photos. Can you do this for videos is an important question. And video is very interesting. If you think of video as set of frames, you actually could miss a very important moment. For example, in this particular video, you're seeing 2 frames. If you look at these 2 frames, you don't know what happened between that. But what might have happened is an important thing, which is a dunk in this case. And that is way more important than the 2 frames that we just showed. So in case of video processing, one of the things you need to do is really make sure that every frame is processed in a way that incorporates the important information. And over the period of last 7 years, we have pushed various video models, basically motivated by spatiotemporal convolutions, which are doing spatial and temporal convolutions together in a factorized way, which is R2 plus 1D. And we also have more efficient models that have higher accuracy but lower compute. What you see here is accuracy on the y-axis and models that we have developed over the years on the x-axis. And the size of the bubble is the compute required. So the smaller the bubble, the better. The higher the accuracy on the y-axis, the better. So as you look at our models that we have been able to push over the last 2-3 years, they have been way more accurate and also at the same time very efficient. And to do this, we again went back to Instagram videos that are public and use the hashtags. Now with video, the challenge is the hashtags have a very, very skewed long tail distribution. So there are few hashtags that have millions of videos, and there are few hashtags that literally have 5 videos, and we still need to be able to train these models. So we actually trained our models on 65 million videos, which is more than 10 billion frames, and we were able to get state of the art on using 200 GPUs, 100 million parameter models on various benchmarks. So these are a bunch of benchmarks on video. Kinetics is the action recognition benchmark, and we were able to get state of the art, a big bump. Epic Kitchens is the egocentric version of cooking and videos with respect to kitchen work, and here we were able to get a significant bump as well in accuracy. So that is weakly supervised learning. I quickly touch on self-supervised learning because this is where the field is right now. So weakly supervised learning is really cool, but it still assumes that you have the hashtags, whereas in reality, many data sets and in many instances, you only have the raw data. You don't have any other supervisor signal or any additional signal that it follows that you can use. In that world, self-supervised learning is really cool and very useful. So what happens in a fully supervised learning realm is you take the data, you label it, you train a model for a particular task. And then on the flip side, in self-supervised learning, you take lots of unlabeled data, typically even 100 times more, because you don't necessarily need to label it. You just take the raw data. And you do this step called pre-training instead of training. And I'll tell you what pre-training is with a much larger model, because these models cannot overfit because of the scale of the data. The smaller data, the more prone the models are to overfit. The larger the data, the better the models generalize and less probability of overfitting. And we pre-train this large model on this large scale of unlabeled data on something called pre-task. So what is a pre-task? I'll give you a few examples of pre-tasks. The idea in all of this is in self-supervision, you're kind of using the context and the structure to make predictions. And in doing this, the structure and context are free, they're free available. You still learn very good representations that will be useful for you for your various tasks. So for example, if you look at text, if you take a sentence, you could basically mask a word and you force the model to predict the word among a dictionary. Now you know what the word is because you know the original sentence. So you can basically, when the model predicts, you can take the difference between the prediction and the actual word, and you can backpropagate and update the parameters of the model and train the model in that way. These models, so this is basically the name of the model that is the best here is GPT-3, are some of the best generative models and text classification models that you can build. Similarly, in images, you could basically mask part of an image and you force the model to predict or fill that hole. And in process of doing that, the model starts learning edges, important aspects, important objects, and so on and so forth. That can then the model then can be used for other image tasks. You can do that for waveforms in speech. And you could do that for more complex inputs like video, where you basically take video of one frames of one video and audio of another, and you ask the model whether they've come from the same video or not. By doing this, you are able to learn really strong representations both in the audio world and in the visual world and use them for various tasks. Why is this so important? What is the value of doing all of this? The value of doing all of this is when you're actually using the self-supervised learning model that you have trained, you can basically take small amount of labeled data and then fine-tune this self-supervised model for various tasks. So if you have a new task, you just take small amounts of labeled data and you fine-tune for the new task. And you keep doing this. The biggest advantage is you can fine-tune for any task you want with very limited amount of labeled data, because the original model has been trained at humongous scale and has already learned the structural representations of the data, which could be useful. So you get significant bump in accuracy, and your training is going to be much faster and typically yields much better performance. So there are a bunch of really interesting works. This particular work, I think, is very interesting because it combines self-supervised learning with vision transformers. So if you look at the evolution of models that are happening in computer vision, we really looked at convolutional neural networks, residual networks, and then we are starting to scratch the surface with transformer models, which have been prevalent in text and audio, and now are making their way into vision. So if you combine self-supervised learning large scale with transformer architectures, you start getting really awesome performances, and the scaling can continue for a while. So that is basically the first part of my talk, which really is trying to touch on how do you build large-scale models in vision, how do you run them in production to support various use cases, how do you actually remove the bottleneck of annotations by using wiki-supervised learning and semi-supervised learning as well as self-supervised learning. What is self-supervised learning, and how do you actually leverage it to learn better representations and then fine-tune for various tasks, and the latest works in self-supervision. Hopefully that gives you a very good flavor of all the interesting things that we are doing in computer vision, interesting models. The second part of my talk is more future looking. If you really look at whatever I have talked already and the kinds of data that I've looked at, they're mostly images, photos and videos that are taken by people more in third person, if not in first person, and shared on the web, and the systems are trying to understand the models. The future is going to be a lot more immersive and a lot more embodied. What do I mean by that? Okay, a lot more immersive because if you really look at the evolution of phones, they didn't have cameras before. They started having very shitty cameras, like small VGA cameras with some resolution that is reasonable to capture photos, but nowhere close to point and shoot and DSLRs. Now, if you look at what kind of cameras we have on phones, it's amazing. We don't only have very high resolution 12 megapixel, 20 megapixel cameras that take excellent photos that are pretty much comparable to DSLRs and point and shoot, but we also start having multiple cameras with depth information, so we can actually start capturing the world in 3D and reliving it and experiencing the geometry and the depth aspects of it. So when we think about computer vision models in future, we cannot limit ourselves to photos in 2D or videos with time. We have to go 4D. We have to go both space and time, and in space we have to go beyond a plane and go into 3D geometry. This is where our Core3D dataset comes in. Now the challenge with doing 3D perception is there are very limited datasets that are 3D. COCO, which is one of the benchmarks in image understanding, has been a big hit in pushing recognition models, detection, segmentation, classification, human understanding, and so on. So motivated by that, which is common objects in context, COCO, we released Core3D, which is common objects in 3D. What is this dataset? So when you really look at the input, there are photos of the same object taken at various viewpoints in a turnstile way, and you're able to merge all of those photos using classic multi-view geometry models to get 3D reconstructions of the photo. This is the problem we are trying to solve. We have multiple input images of a thing observed from various viewpoints, and we want full 3D reconstruction of the object, which we can then use for various purposes. The number of applications are unimaginable. The list can go on, but here are a few. You can take the 3D object and render it in augmented reality, so you can visualize the furniture that you want to buy. You can automatically convert 3D and represent, digitize the world, especially the historic world that we want to preserve forever. You could do virtual try-ons. So in this case, you have the cute puppy and you want to know how will this, I don't even know what it's called, a shirt, a pant, whatever it is, and you want to visualize how the puppy looks in that. And you can do all of this if you are actually able to get the 3D models of those objects and render them. But learning 3D object categories is extremely hard problem. And it could be hard in many ways, especially if you are thinking about learning 3D object category, learning 3D representation of a category that looks visually different. So in this case, you have different fire hydrants, and you want to be able to still reconstruct in 3D how does a fire hydrant look. There are existing works. Our work is not the only unique one by any means, but these existing works are on different parts of the spectrum. So if you look at y-axis as the amount of supervision you have to train models, and if you look at the difficulty of training these models as on the x-axis, you have ShapeNet, which is all synthetic data. So you have 100% supervision. You know everything about each pixel because it's synthetic, and you control the rendering. But the task is not as difficult because it doesn't have real world deformations and real world irregularities. On the flip side, you have real isolated views of different objects. This is birds and Pascal VOC, but you don't have as many annotations, so you don't have a lot of supervision. So task is very difficult, but you don't have supervision to train models on. So what we are doing is trying to fill the gap in between with Co3D, where we are basically trying to generalize as many views as possible for various objects, but give enough structure to the data so there is supervision that can be used to train models. And that's where Co3D is. So we crowdsource to collect turnstile videos of day-to-day objects, like in this case, banana, apple, orange, and so on. And the user, the crowdsourced user, basically captures that video in a turnstile manner, and this raw data is what we use, and we are able to automatically do structure from motion to get the camera position for each frame, and also the point cloud of each of the objects that is captured, so we can get 3D models. And we are able to collect this for many categories. Here is a set of categories and examples collected videos for fire hydrants, for teddy bears, for cups, benches. And if you really look at the real world data sets, like I said, ShapeNet is synthetic. Co3D is the largest real world data sets with thousands of objects and many number of videos for the same object, which is very important. So that's a comparison. The way we do it is we basically take the raw video and we do SFM, structure from motion, where we're able to get the camera viewpoint as well as the point cloud at the same time, and we're able to do it for millions of videos. This is an example camera tracking for various input videos, so the teddy bear, the glove, hot dog, and fire hydrant. And you see in what the algorithm is doing is actually triangulating the camera position and at the same time building the 3D model of the object. So this is like broccoli, fire hydrants, motorcycles, and so on. So this Co3D dataset is publicly released. You can actually download it, build models, and we're going to release version 2 soon, which has even more objects, even more annotations. What does this enable? It actually, this kind of data set and benchmark enables us to go after models for various tasks. For example, here is task 1, which is reconstructing independent objects. So what we are doing is you get a video of a single instance, and your job is to get a 3D reconstruction from that video using a model. Second, you can learn 3D object categories. So you look at various apples, green, red, more ripe, small, big, and get a sense of what could a model or 3D model of an apple look like. Now that 3D model of an apple is a generalized version of the apple. It need not correspond to exactly one instance of an apple, but that generalized version can then be used for various purposes. And you want to train a single model that incorporates all of these videos and produces this single output, reconstruction output. Then you have a third problem, which is few reconstruction. So you just take few examples, not a lengthy 1-2 minute long video. And just with those few examples, in this case 8 examples, you are able to do 3D reconstruction of that particular instance. So this is a benchmark. We're really excited about Co3D. We believe that this will supercharge the research in 3D perception and allow us to bring a lot more things in real world to digital world, because we are able to generate 3D models of them with ease, and we will have better and better models over time. The second part, the benchmark that I want to introduce, is Ego4D. Now, when you really look at how the world is moving, it's not going to be too long before people have wearables with sensors. Meta, Facebook recently launched in partnership with Luxottica, Ray-Ban. These Ray-Ban stories actually allow you to capture photos and videos, important moments of your life, allowing you to also listen to music on the go and so on and so forth. But when you capture it, you're capturing it from your viewpoint, from an egocentric viewpoint. which is the first person viewpoint. So what Ego 4D is trying to do is create world's largest egocentric benchmark to build AI models. This is a large Ego 4D team. There are obviously a lot of people in Facebook AI and Meta AI that are working on it, but this is in partnership with 12 different universities across the world. When we really started this project, we wanted to make sure that we get a uniform representation as much as possible from every part of the world, so the models are not biased and we are able to build models for everybody. And what this benchmark is trying to do is push the frontiers of first-person perception, learning and inferring from disembodied photos and video, which is the current status quo. If you really look at the photos and videos today, they are taken mostly from third-person point of view, not from a first-person point of view. That's disembodied. Whereas when you really think about robotics or wearables with AR glasses, they're all going to be first-person point of view. And even if you really look at self-driving cars, the camera that is looking for the self-driving car, it's looking from first-person point of view, from the point of view of the car. So the first-person perception is an important problem that we need to tackle to actually build applications of the future. And there's a huge difference between a first-person view and third-person view. So here you see two examples. In a third-person view, you basically see the whole scene where the camera is mounted somewhere. In a first-person view, you get really what that person is actually looking at. In this case, they are looking at that person in the booth or the coach store and so on and so forth. So it reveals much more important information of the attention, and it also gives us a very personalized view of what the so what we are trying to do is push egocentric perception for augmented reality systems. This will be useful for robotics, and it's again, like I said, everything that we do, it's not we are not the first to do it. There have been many efforts in egocentric perception. Here are a few, but each one of them has some shortcomings. Either it's the scale, the diversity, or the vocabulary being limited, the length of videos, the sensors that they were used, and so on and so forth. So what we are really trying to do with Ego 4D, and the name Ego 4D is egocentric data collection in 4 dimensions, that is 3D plus time. The goal is really scale the number of hours to thousands of hours from hundreds of different people with hundreds of scenes. And this is something that has not been done in history. And we really have been fortunate to be able to pull this off over the past couple of years. And we released Ego 4D. This is world's largest first-person video data set to our knowledge, with more than 3,000 hours, 3,400 hours of video, almost 1,000 people capturing it. And they're capturing daily life activities, not special things like cooking and so on. It's basically everything that they're doing in their lives. And we are actually creating a benchmark set of challenges on top of this data set, so people can actually keep pushing the models and compare how they're doing with respect to each other. The timeline, this began in late 2019. We released 2 months ago, and we are hosting the challenge next year in ICCV. This is the whole consortium, universities across the world coming together to pull this off. And here are the example daily life scenarios of the videos that are in Ego 4D. The entire idea is to capture unscripted daily life activity, so it doesn't feel artificial. And we gave full freedom to people, to the users, in terms of what they want to capture. So they have used various kinds of hardware, GoPro, Vuzix, and so on and so forth. When we did this, it was very important for us to do it in open, to make sure that we get right permissions. So we have modules that de-identify people, de-identify license plates and important numbers, and each frame of every second of every video goes through these pipelines to make sure privacy and ethics compliance is of top priority. And each partner underwent through this, and we went through months and months of IRB reviews to make sure this is done in the right way. And we have consent forms of people who are actually recording. And as I said, we actually de-identify faces and important information to make sure that there are no surprises. And they're like, it's humongous scale, 3,400 of videos, thousands of people, 1,000 people, 1,400 hours of audio, and so on and so forth. Here is a small set of examples in terms of what the videos look like. So this is a person capturing a video of them probably doing their commute on motorcycle or going and shopping something. So you see the video from their point of view. This is a person in the lab doing some experiments. again, you can clearly see what their focus is. They're actually cleaning a particular equipment. They're wearing gloves, so they're following safety precautions. So you, instead of third-person video, which kind of captures everything, in first-person video, you really know exactly what activity they're focusing on and what is a task they're doing, which is very unique and interesting. So we also have 3D scans of the data. So in some cases, we have 3D Matterport scans. So we have full 3D geometry of the view. We have eye gaze in some cases. So we know what the user is focusing on and the ground truth. So we can actually build models to predict it and compare. And this is publicly released, as I already mentioned. So we are actually going to host a bunch of challenges with respect to Ego4D. So these are 5 challenges. I will quickly talk about it. One of them is episodic memory. It's like you can answer questions: where did I leave my keys? Where did I leave my wallet? So you have to track objects, represent them, put them in 3D. Hands and objects is like, what am I currently doing? Am I cooking? Am I drinking water bottle or eating or drawing, etc., etc. Forecasting, which is trying to predict what might happen in the future, a few seconds down the line. Audiovisual diarization is who spoke what, when, so you can kind of reference the conversation again and maybe have reminders saying, hey, you promised to call your mom and wish her birthday. Or you can talk about social interactions. It's like, who are we interacting with? What is the emotion? Are you trying to accomplish a task? And so on and so forth. So if you categorize them, they're basically the related to places, objects, and people, which is kind of a high-level way of thinking about various challenges. So I already mentioned this. I don't want to go into the details. So this hands and objects task, forecasting task, and then we have the audiovisual and social tasks, which is trying to do diarization and trying to understand what people are doing in the videos. Upcoming milestones, we launched it. We are going to hold a competition in 2022. So if you are a vision researcher participating, you might want to train models on this and showcase how your models are better than other models. We'll have a leaderboard and we will see which of the models do really well. Here is the license. And with that, I hope I gave you a really good overview of how to build large-scale models and run them in production, and what are the efficient ways to do it, how to remove bottlenecks in annotation to move towards self-supervised learning, and how to move towards 3D perception and embodied AI, which is where the future is, and what many of the models need to do. And hopefully that was useful. It was a pleasure talking to all of you, and I'm more than happy to take any questions. Thank you.
Thank you, Manohar. That was some really good presentation, impressive and fascinating work, right? Understanding the world through computer vision, right? Not just still images, but understanding the activity of what is going on around that image and the videos. That's some really impressive work. So I'm not a specialist in the field, so I'll do my best to translate the questions in such a way that makes sense to you. And if the folks watching on YouTube have more questions, please post them on the chat, and I'll translate them to Manohar. So when you started the presentation, I was asking myself if you could, what you're doing to images, you could do to video. And then you said, you showed that you can do it to video. Then my next question was, can you do it in real time? And you showed that pretty much you can, right? And the following question was, can you do something that's better than the ill-fated Google Glass, right, to augment reality? And then you show that you're getting pretty much the information from Google Glass, you're augmenting the world with information. So you pretty much answered all the questions I had. But what has changed? What has changed that allowed you to move forward so much when previous attempts didn't go so well?
It's a great question, and I think we should decouple that into multiple aspects, right? So there is the hardware aspect, and there is the technology, like modeling and capabilities of these AI models. There is a data aspect, and there's just expectations of people. For me, I think hardware, we continue to make progress on compute. We continue to squeeze more and more things on silicon and chips. So if you really look at Ray-Ban Stories that was launched this year, it's a piece of art. I mean, you take Ray-Ban, which is the iconic style that everybody wants to wear on their face, and you kind of extend it to have microphones so you can listen to music on the go, and you have 2 cameras that are actually able to capture. So when I wear them with my kids or at home or even outside, one, I use them for running and listening to music, so I don't have to have AirPods that might fall off. It's basically glasses that you wear. And second, you can quickly capture a moment without taking your phone out and get the camera on and so on and so forth. So there has been a significant amount of progress in hardware. So that is something that will continue over the next few years. There has been a lot of progress in AI models. If you really look at what was possible even 4 or 5 years ago, many of these AI models could not recognize more than 10 actions, 5 actions, 100 actions. They could not run real time on these devices because they would take GPUs and they would take a significant amount of compute. They would need a tremendous amount of annotations to build the models. So we have been able to reduce the number of annotations to build models. We have been able to increase the vocabulary that these models understand. And we have been able to compress those models to run real time on very small amounts of compute. So those are the things that have changed. But honestly, it's at the beginning. I would not be surprised if we continue to 2x the vocabulary of things we understand. We continue to 10x the latency requirements. I think the biggest challenge is actually thermal, because when we wear these glasses, we don't want them to get super hot. To me, I think that's the biggest challenge that we'll have to tackle. The rest of the challenges do exist. There's no doubt about it. And of course, the price point. It's going to, when we really bring that into consumer grade, that is only where we can actually reduce the price point. So if you really look at what we have in VR glasses with Oculus Quest, it's amazing that these devices are less than $400. Just 4 years ago, they started at $2,000, $1,500. And now you're getting the best VR experience possible under $400. So I think that's what has changed. The technology we have continued to push the technology. We've continued to push the AI frontiers. We have continued to squeeze more and more compute capabilities and reduce the price points and give specific features. I can't really comment on Google Glass necessarily in terms of what their product line was, but when you really look at Ray-Ban Stories, the product appeal is very clear. You want glasses that are stylish looking, but you also want to augment the capabilities by actually listening to music on the go and ability to capture photos that are real-time moments without missing that moment. Right? There's a real product market fit here in terms of how to think about it, rather than, hey, this is an augmented reality glasses, you'll do cool things about it, but what are those cool things? You figure it out. There's a difference between the two, in my opinion.
Nice.
It's a great question.
Yeah, thank you. So I have a question from the public. He's asking, first, thank you for the great talk, and asking if you have plans to employ this technology to assist visually impaired people. Yes, you have something, as you described in the beginning, but together with videos processing.
Yeah, it's a great question. Accessibility has been near and dear to my heart. I still remember the first research publication I wrote, which was around seeing text in videos. And I remember writing this statement is like, we really want to make sure visually impaired and blind people also have the same, at least similar experience with richer metadata, richer data like photos and videos. And that is something that I hold near and dear. So as we are pushing this technology, that is one of the reasons why Facebook was one of the first companies, if I remember right, launching automatic alt text. Everyone else had this feature in the lab, like prototype and so on. But Facebook was really the company that said, we're going to launch this, we're going to enable it for millions of people who use Facebook. So Facebook is used by billions of people, but there are millions of people who are actually visually impaired. And this feature has been a game changer for them, to be honest. And we even won the FTC award for doing that. So we continue to do it. The part that is most interesting to me for visually impaired in embodied world is when these glasses with accompanying compute have enough capability to do this in real time, where the visually impaired person or accessibility, the requirement of accessibility has a real-time conversation. It's like, hey, it proactively says you're not doing something safe, or you are quickly answering a question is like, you should not eat this because you're allergic to nuts, or hey, you forgot to close your garage door, or so on and so forth. Right? These are really like simple things that we take for granted. Even for us, we forget, but for a person who is visually impaired, they're life and death. So this is definitely something that we are keeping an eye on. It's early days. The problem is you want to make sure that the accuracy of your models is very, very high. Because for me, if the model gets it wrong, I can verify it and I'm saying, okay, hey, that's wrong. But for a visually impaired person, that's their ground truth. If you say you can safely walk forward, or you can pick that up, and it turns out instead of an apple they pick up a knife. That's a pretty big deal, right? So you want to really make sure these models are very accurate before you launch more in production or in real life. But this is definitely something that we are looking at, and over time we will continue to build models and build experiences for accessibility.
Nice. So related to the idea that you have to update these models to correct problems, right? We have a question from one of our colleagues. She's asking the following. So today it is very important to design scalable systems to deal with images, but an important question is how to incrementally adapt decision models to classify new images, to recognize new persons, new kinds of objects and such, which are not available at the training step. Do you think the computer vision techniques are prepared to deal with this challenge?
Great question. Thank you for asking it. This is an active research area. I mean, it's called incremental learning. There's another way to look at it, lifelong learning. You have to break down this problem into multiple things, though. One problem that is brought up in the question was, how do you adapt to the changing distributions? So there could be new. So you can see, like, let's say, just magically out of thin air, from tomorrow onwards, everybody decides to dress their cat, just for whatever reason. So whenever you get a new photo of cats, they're all dressed, and you have trained all these models with cats that have not been dressed. What happens? Your accuracy is going to fall dramatically, right? So what we need is models that adapt to the distribution of the changes of the world over time. So that is definitely one research problem we are actively looking at. The second problem is out of distribution. So I remember there was this funny thing that happened back in 2015, if I'm not wrong, or 14. I don't know how many of you remember this. It was called Ice Bucket Challenge, where famous celebrities would basically pour frigid cold water on themselves for various causes. And we had no such category. And out of the blue, people started uploading millions of videos of Ice Bucket Challenge. And we had roughly 4 or 5 hours to train a new model. So what I showed today, if you read one of the nice things about neural networks is you can train branches on top of these existing representations with new data. So you can quickly incorporate new classes, albeit at lower accuracy, but still you can do a good job of detecting them for things that that are coming from out of distribution or that are novel. So that is an active research topic, which is how do you incrementally learn instead of learning the whole thing again? How do you incrementally learn for new classes is the second research problem that we are looking at. And the last one is a combination of the two, which is few shot learning. For good or for worse, humans are amazing, have the amazing ability to generalize. So we don't sit and teach our kids, here are 1 million cats, here are 1 million dogs, here are 1 million cups. We basically teach them a cup has a handle, sometimes the cup doesn't have a handle, sometimes the cup breaks. And they just, by interacting with the world and by getting some sparse samples from their parents and their friends and seeing and observing the world, they're able to learn and generalize very quickly. So if for whatever reason Crate and Barrel or a new company came up with a completely new way of designing a cup, I bet you more than 95% of the people will still quickly say that's a cup, even though they have never seen that kind of a design. Why is that? Because we have this notion that a cup holds certain things, it could have this convex shape, and so on and so forth. Whereas the current models, they don't work that way. The way they work is, give me 1,000 examples of cups, and this 1,001 example looks similar to this, so I will classify it as a cup. If something doesn't look similar, then I kind of fail, right? So what we are trying to do is push on this research on few shot learning, which is basically trying to understand the underlying structure and understand the affordances, and then try to generalize as best as possible with very few examples. All three of these topics, incremental learning, adapting to the distribution changes, few shot learning, these are all active research areas, and neither Meta nor any of the academic labs have cracked the code. And I think it's going to take us decades, if not more, to keep making progress in this.
Nice. On that front, right, you have shown that you have many collaborations with universities around the globe. How do you get into that list? We have many academics, students, professors watching.
No, it's a combination of, so we always put proposals out to solicit interest from across the globe. That way we don't have a confirmation bias or a historical bias that we have worked with certain people or certain universities and we continue to only work with them. So that's something that we do. We put call for proposals, as I said. Second, we also pick where is the best research coming for a particular area. So if you looked at the 10 or 12 universities that we talked about in Ego4D, these are the labs that actually built egocentric data sets. These are the labs that published the best papers in egocentric perception and have been leading the charge. So partnering with them actually allows us to bring the best people working in a particular area. That could be in egocentric perception, that could be in 3D perception, that could be not even in computer vision, in language, in translation, and so on. So depending on the problem, and in some cases, for example, with connectivity, we actually partnered with universities in Africa, in India, because many of the efforts there are needed to be adapted to the data that are coming from those places, even though it might be very easy for us to partner with a university right next to us, like Stanford or Berkeley. But it really depends on the problem. It really depends on what expertise each of these universities bring. And it also depends on who is excited for our call for papers and put proposals. So we actually try and do our best in casting a wider net and collaborating with as many people as possible. At the end of the day, there's a lot of interesting work happening across the world. And that's one of the reasons I'm actually talking and giving a talk to you guys, because like I'm absolutely sure there'll be a lot more ties with South America, with Brazil, with your university, and hopefully more people who are working in, especially in computer vision, which is my passion, reach out and we partner even more. We're always looking for more partnerships.
That's really good to know. We do have a couple more questions from the public, if that's okay with you. Okay.
Sure, let's go for it.
So many thanks for the talk. How do you check and evaluate the correctness of the labels assigned through the semi-supervised learning in such a large-scale data?
You don't. That is the beauty. So in the entire point of semi-supervised learning, so in weakly supervised learning, you don't. In semi-supervised learning, you do have large data, but only part of the data is annotated. Because part of the data is annotated, it's not as large scale, you can actually validate. So the way we validate is we have human annotators and reviewers, and we even have multiple of them looking at the same thing, and we do cross comparison and we do histogram binning. So if there is multiple people and there's a lot of entropy, then we discard that label. And if there are multiple people and they're all saying the same thing, then we have high confidence on that label. And that's what we incorporate when we train these models.
Okay. One last question. So foundation models are trained models on broad data, generally using self-supervision at scale, and that can be adapted to a wide range of downstream tasks. Recent studies have provoked intense debate about these models. Has Facebook Meta investigated this kind of models?
Great question, and it's definitely an active research area. So the core question, probably without them explicitly stating it, probably they're still stating it, is what are the biases of these models? By actually training them at large scale, are you amplifying the biases, or are actually generalizing these models so they work well with many kinds of data from various locations and so on? So the real answer is we have published some papers. We are actually trying to have our findings and share with the community. It's early. In some cases, we have seen the biases amplify. In some cases, we have actually seen the biases reduce because you are able to train at such a large scale, and the models are actually looking at various kinds of viewpoints and so on. What we have learned, though, that is very concrete is whether you're doing fully supervised learning, self-supervised learning, weakly supervised learning, you should make sure that you have geographic diversity on the data. You have ethnic diversity in the data. You have gender and age diversity with respect to people. You have, let's take text, you have font diversity, size diversity of font. So there is no silver bullet in terms of building generalizable models other than making sure that the data that you use to train these models have a wide representation. So you are actually doing a better job. Now the catch is at test time, what are you measuring the accuracy on? If your test set is biased, then your model that is trained on generalized way is going to do worse than a model that is overfitting to a specific slice that is in the test set. So it's really, really important that you are scaling not just the training data, but you're also scaling the test data. You're uniformly sampling across geographic location, ethnicity, race, gender, and so on. So you are doing a good job of training the models on diverse set of data, and you're evaluating the models on the right test data. This is really, really critical. But the core research question that is yet unanswered with clarity is, when you keep scaling the data blindly, does it amplify the biases or does it reduce the bias? In some cases it does, in some cases it doesn't. Sadly, that is the answer that we have to live with today until we do more research.
Excellent. So I'm sure we could go on for hours and hours discussing this topic. It's really fascinating work. Unfortunately, you have to finish the session. So I'd like to thank you again so much for this talk.
Thank you, Lazaro. Thank you, Lazaro, for having me, and thank you for great questions. These have been some of the best questions I've had. It clearly shows that the audience is very well read, and hopefully the talk was still useful for them. And I'm really looking forward to awesome work coming from that side world, and hopefully at some point I could do this in person. I have always wanted to visit Brazil and all the amazing things that are happening there. Good luck, stay safe, and thank you for having me.
Thank you. We'll be open to receive you. Okay, with that, I'll stop the streaming.